let's start. Welcome everyone to our first developer edition of Bitcoin Tuesday. And today I have with me my colleague at Boltz, Michael, who will talk about Taproot and how to do swaps using Boltz. So Boltz has an API, and today we will slowly go through the basics of Taproot, and then after the slides we will see a little demo, and then you do the demo on your computer doing a swap via Boltz. All right, Michael.
All right. So, hi everyone. My name is Michael. I work with Kilian at Boltz. I mainly do development and backend development, and I work with on-chain scripting, lightning payments, and pretty much all the operational stuff to move Bitcoin around. Today's topic is connecting the Bitcoin layers. And what we mean by that is there's not just the main chain. Like, we all know the main chain, the Bitcoin main chain, which has a block every 10 minutes, new coins get created, all the shenanigans. That's what we call the main chain, but there is much more than that. We also have Lightning, Liquid, and Rootstock. Lightning is the payment channels. I think everyone has heard of that one too. And there is also Liquid and Rootstock, which are side chains. So they are also blockchains, but they are connected to the Bitcoin main chain. In a sense, they are using Bitcoin as a money, but they have different properties and behave differently to Bitcoin. For example, Liquid is very much like Bitcoin, but it has extra features, like for example, confidential amounts and transactions, which means that you can't see the amounts that are being sent around, and also some additional opcodes, which are operations you can execute on-chain. On Bitcoin, we have like a very limited set of things we can do, and if you're into Bitcoin development, you probably know every change in Bitcoin is heavily contested. Changes only happen very slowly, and when we have a chain like Liquid, people can experiment much more easily because it doesn't matter as much. If something breaks, yeah, things break. The Bitcoin is still fine, but Liquid can play around and experiment with stuff. Rootstock is another such example where you have a chain that's connected to Bitcoin and uses Bitcoin as money, but operates differently on the side chain. On Rootstock, we have a very similar chain to Ethereum from a programming perspective, but the money that's on the blockchain is still Bitcoin. The issue is now that moving your BTC around all of these different solutions is really annoying. Like we all know, on Lightning you have the problem with inbound capacity and outbound capacity. You have to open your channels and whatnot. And on Liquid and Rootstock, there are so-called bridges where you can give your BTC into the bridge on the main chain, and after waiting for like a day or two, you have the coins on the side chain. Really bad user experience, and that are things we want to address. These are things we want to fix, and we want to make payments flow across all the different Bitcoin layers, up, down, and sideways, really easily for the user, just like one click, 1 cent, done, fast, and also reliable. That's the mission statement for us. The question is now, how do we do that? These are all different blockchains, and Lightning is even something entirely different. What is the common denominator that we can use everywhere to connect them? And the magic sauce here is HTLCs. HTLCs are hash time lock contracts. So basically a smart contract with two conditions, either a hash lock or a time lock. So these are the two primitives we work. A hash lock means that a secret is revealed and the coins can be spent. A time lock is some amount of time passes and coins can be spent. And with these two primitives that are fairly easy, like a hashing function or a time lock, which is basically like a timestamp comparison, these two primitives are available everywhere on the main chain, on Lightning, and on Liquid and Rootstock. And with these two primitives, we can connect all four of them because they are available everywhere, and the common denominator between all of them. When we look at how payments work on Lightning, we have 3 Lightning nodes, Alice, Bob, and Carol. And if Alice wants to pay to Carol, what effectively happens is HDLCs are created. Every payment on Lightning is an HDLC. So when you pay, and Alice pays Carol, an HDLC goes from Alice to Bob and Bob to Carol. It's basically a step-by-step, and every hop on the route creates a new HDLC. When Carol accepts the payment, the hash lock is used, and Carol reveals a secret that goes to Bob, that goes to Alice. So the hash lock path is used. In case Carol isn't responsive or just doesn't want the payment, she can reject it, and the time lock path is used. So basically, after a certain number of blocks or a certain amount of time passes, the payment just reverts back and the money goes back to Alice. So we have the two paths. Either everything is fine, a secret is revealed, and the hash lock path is used, or in case someone is uncooperative or doesn't want the payment, the time lock path is used. And like after a certain amount of time, everything goes back to where it was initially. Basically, revert back to status quo where we started with. Now what we do is very similar in the sense that Alice wants to get the Lightning funds on the main chain, back to on-chain BTC. And what effectively happens is we have the same starting point as a Lightning node, and they send an HDLC on Lightning to us. But we don't forward the HDLC to another Lightning node, we forward it as an HDLC on-chain to the Bitcoin main chain. And you can substitute the on-chain part to liquid or rootstock, because we know that these HDLC primitives with the hash lock and the time lock, they exist everywhere. So we can forward the HDLC on the main chain, on liquid, on rootstock, or pretty much any chain or network where the hash lock and the time lock are possible to implement.
Let me do a summary.
Yeah, sure.
En resumen, ¿qué significa? Si quieres hacer un swap entre una capa de Bitcoin y otra, la tecnología que conecta las capas son los HDLC. Es la misma tecnología que está respaldando el red de Lightning. Este es el subir todo el y que hace Boltz es muy parecido de un pago de Lightning. Si Alex quiere pagar a... si Eres quiere pagar aquí, hace una transferencia en el red de Lightning a través de Boltz. Y nuestros swaps funcionan en la misma manera, solo que aquí no hay nodo de Lightning, aquí hay una cadena, que puede ser la cadena principal, que puede ser rootstock, que puede ser liquid. Pero funciona técnicamente exactamente de la misma manera.
Yep. It's the exact same concept as a Lightning forward, just that we don't forward to the Lightning node, but to the chain. See.
If Lightning finally adopts UPLC instead of HDLC, how would you change the architecture?
When that eventually happens, you would have to switch from a hash lock to a signature, basically, a signature check. That's, yeah, simple enough. It would depend on the implementation details of the PTLCs, which are not super final yet, but in the end you would rip out the hash lock and use a signature check instead.
Which are the advantages of using that instead of closing a Lightning channel?
Yep. When you go to the main chain, you could just close the channel and use the coins then. But when you close the channel, you don't have, the channel is gone. When you pay someone and then swap to on-chain, you have inbound capacity. So basically, it's for the main chain, it's a way to get inbound capacity, and also that's the main thing on the main chain. And when you work with liquid or rootstock, you can't just close it, because there is, would have to bridge and wait 100 blocks and wait forever. It's basically, it allows you to get inbound, and also that you can go to different chains. Also, you're a little bit more flexible, because you can do, for example, with this you can do a multipath payment, and to use multiple channels for one big swap to on-chain, but keep the existing channels and have lots of inbound in just one on-chain transaction. That's the advantage, that you have pretty much more options as a Lightning node runner than just splicing or closing.
So for example, you have one Bitcoin,
yeah,
and you only want to put half of it in the main chain, okay, you can do it without closing.
Yeah, exactly.
And what you do by that actually is, when you put it on the main chain, what you actually do is you move half of Bitcoin to the other side of the channel. Like
It's just a lightning payment, basically, yeah.
You create inbound liquidity, this is what Michael said. This is the thing most people use our service for, is to rebalance their channels to have inbound liquidity, because it's very hard to get inbound liquidity. Splicing cannot do that. Channel closing, your channel's gone. You don't want that, right?
And you have to pay the fees.
So this is the only way how you can reliably get inbound liquidity.
Either you buy channels or you swap to on-chain. Yeah. Like that's the one way to do it, and that's pretty much the way to do it, because if you look at all the merchant nodes, like for example, smaller merchants selling stuff on BTC Pay server over Lightning, what they do is exactly this. Not only via Rust, there are alternatives too, but when they get lots of payments, balance starts to accumulate on their side of the channel. They just move it all to the other side with one swap, and they have lots of inbound to receive again. I hope that answered your question. Yeah, okay, perfect.
So in Boltz, you have to be doing channel rebalancing all the time, or you have very, very big channels, or...
Short answer to that. So at Boltz, we are very much, ourselves. Basically, you're saying if people do that, our channels get imbalanced.
Yeah.
That's technically true, but we are in a luxurious position where our node is very big. So we actually forward a lot of volume, which makes us a very attractive point or a channel node to open a channel to. So what's actually happening is that small nodes open channels to us because of the volume. They do a business forwarding payments to us, and they actually rebalance themselves. They do it themselves. So it's organically rebalancing for us. Not 100%, but more or less it's okay.
Yeah, basically because...
You don't have to do much to get inbound liquidity or...
Yep, true that. So when we have this on-chain HDLC now, we have to actually create it, because a normal address that you create from your wallet is not an HDLC. You have to do custom scripting to allow for the HDLC to be on the Bitcoin chain. And in our first iteration of the swaps, we used SegWit v0, so basically the first SegWit version, and we used this script. And basically what it says is, there's an op-if, so an if statement. If the hash is correct, op hash 160 executes a hash on the Bitcoin chain, and then op equal verify verifies that the hash is correct and what it's supposed to be. And in the else case, like op if, op else, there is a time lock, which is the operation op CLTV, check log time verify. And depending on which condition is true, we push a public key on the Bitcoin stack and in the end verify the signature. So basically you have two ways of spending addresses based on this script. In a normal Bitcoin address you have in your wallet or Bitcoin Core, you have a signature check. One private key, you can spend it. In this, it's a little bit more complex, that you either give it the correct preimage, the correct hash lock, and fulfill the hash lock requirement, and have the correct key, or you wait for a certain amount of time, the time lock component, and have a different key with which you sign the transaction. So basically the two concepts, the hash lock in the if, and the time lock in the else, and then a signature check. So it's not only a signature, like a normal Bitcoin address, it's an additional condition. And that was our Bitcoin script until very recently. But then we worked with Taproot. Taproot is like the latest Bitcoin soft fork from 2021. And with Taproot, you can be much more intelligent about how you script, because this is it's an if and else. It's not very beautiful, it's not very efficient on-chain, and it's not very good for privacy, because when you reveal the whole script on-chain to prove you can spend it, everyone gets to see what's happening. That's not very good for privacy, and also it requires a huge amount of on-chain space.
Is that clear though, the hash lock and the time lock, how that works? Is that understood? Yeah. Hash lock, if everything goes as planned, we reveal the secret, and the payment will flow, the swap will get executed, and the time lock is like if something goes wrong.
Yeah.
If something goes wrong, money goes back to the sender.
But like for the whole thing to be trustless, you have to have both conditions in the address and have to always use the full script, which is bad for privacy, uses a whole lot of on-chain space, so it's expensive for fees. And we have a better option now with Taproot. And with Taproot, we can be much more flexible in how we reveal which script to execute on-chain, and we even have a way of creating hidden multisigs, and we're going to talk a little bit about that now. First, music 2. With Taproot, Bitcoin switched from ECDSA to Schnorr. So we switched the underlying signature algorithm, the way signatures are created and verified. The complete algorithm was switched out from ECDSA to Schnorr. And Schnorr signatures are much more flexible when it comes to tricks and where you can modify and use them. And one such example is music 2. In music 2, we can do a neat little trick where we have one key of a flaky HDMI cable, one key of us as a service, Boltz, and one key of the user. And those two keys we can use to create one common key. So basically we have two keys and we combine it into one. And that one key is basically a multisig of the two of us, but
It's only one key.
it's only one key. It looks exactly like a normal single signature key, so in a sense it's a hidden multisig. To the unknowing observer on chain, it looks like a normal single sig. You can't tell if it's a multisig or what's going on behind the scenes. It's just one normal key. And that normal key, to be able to create a valid signature for it, you have to have both keys behind the scenes. But when you look on chain, it's just a normal signature. You can't tell, the unknowing observer can't tell what's going on. And that's a really beautiful thing about Schnorr, Taproot, and music, that it's like a super chain efficient. You only need one signature to spend, and also privacy preserving, because an unknowing observer like Chainalysis or someone checking out the block explorer can't tell it's a multisig. It's just one key and one signature to spend. Yes.
Music 2 is the protocol to make the merge between the two
Yes.
private keys or the two public keys?
Exactly.
One?
That's what the protocol is called to do that. There are different ones. There's also like music, the first one, music 2 and music DNF, but like the most common one is music 2, and music 2 is like battle tested by now. It's been around for a couple of years, and it's going to get merged into Bitcoin Core itself very soon. So it's a really stable protocol you can build on.
Interactive protocol.
Yes.
Yes.
When you have these two, like to create the aggregated public key, we just have to exchange public keys. When we want to sign together for the aggregation, it's an interactive protocol where we have to do two rounds of communication, one to create the common aggregated public key and one to create a signature and aggregate it too. Like it's an interactive protocol, just like a legacy music with a script would be. There you also have to communicate. But here it's also an interactive protocol. Like you don't save interaction, you just save on-chain fees because it's much smaller than a normal multisig, and also it's better for privacy because it's just a single signature and a single public key.
Just to know that we are on the same track.
Yes, exactly.
It's more interaction, no?
Like it depends on how you do it, but like if you have this kind of interactivity, it's at least 2 rounds. If you do a legacy multisig with a script, it's also 2 rounds. Yeah, like you don't have any real downsides apart from it being newer tech. Yeah, and it's not as well adopted yet. It's going to be in Bitcoin Core soon. There's an open PR for it. There's going to be wallet descriptors for it. So it's getting adoption slowly but surely, but it's coming. So it's a really cool new thing that's coming soon.
That communication between to create the server key, how do they put in contact, or how do they complete a transaction, or it's very made out of the protocol?
Like in the end, you can communicate however you want. In our case, it's a REST API, so HTTP calls, but you can do it peer-to-peer, you can do it via a USB stick, you can do it however you like. There's a limitation regarding that. It's just about, and it's very little information you need to share. So it's very easy to do and you can use whatever you like. So there is no limitation to that. You just have to do it. How you do it is up to you. In our case, it's a REST API. All right, but we've just...
Please understand what multi-music to means, because this is very important.
Yes.
The base of
The base of everything we do with Taproot.
The two keys used to make the killer key are private keys or
Public keys. In the end, like Boltz has a public key, and you have a public key, both have a private key, but we need to share public keys. Like everyone keeps their own public key to themselves, but shares the public key, and we only share public information. The private key always stays with you and only you, which means that if I want to sign something together that you don't want to sign, it won't happen. So your private key always stays with you. We only communicate and interact in a way that shares public information that you can't.
watch the others.
No, I can't force you to sign. We just we have to agree, like with a normal multisig, that we both want to sign. Then we communicate, and then we can sign together or aggregate together. There is no sharing of private keys.
Okay. As a general rule, you do not send private keys no more. They always stay with you.
Yeah.
So first you send the public keys, aggregate the keys, and the second one is you sign them with your private key, but you sign it privately, and then the sign thing.
Exactly.
The links of the public key.
Okay. So first of all, we take the public keys. We just take the public keys, we communicate them, the public keys, only public keys, and aggregate them. When we want to sign, I take my private key, sign, give you my signature, you privately sign with yours, and then combine those two signatures into one. So the private keys always stays with whoever owns the private key, and we just communicate either our public key or it's called partial signature, our part of the signature, and when someone has all of the parts, they can combine it into one. Yeah.
That's the beauty of Schnorr, by the way. Schnorr enables all of this. Before it was not possible.
Yeah.
You could not take two things and put them together and they would.
Like
I suppose there would be many libraries implemented that key or signature is changed. Verify it, or you have to do. You've done the key signature and all of that by yourself. There are some libraries implemented by, I don't know.
Right now there are two libraries that are production ready that implement music too. It's BTCD from Lightning Labs, and it's the SecP fork of Blockstream called SecP 256K1 CKP.
We can send the links.
We can send you links in C.
The latest one, I know it.
Yes, and it's also going.
It implements that.
Yeah, it implements that, and it's coming into the upstream, the Bitcoin Core version of SecP very soon. There's an open PR, and it's the same as in the Blockstream version, just a little bit cleaned up, but yeah.
The other one is implemented in Rust, I suppose.
BTC is in Go. Yeah. Okay. Like one in Go, one in C, and it's coming slowly. It's been a while since the Taproot, since the Taproot hard soft fork, but normal Schnorr signatures are very common to use in lots of libraries. These aggregation things took a little bit longer, but they are slowly coming. It's coming to Bitcoin Core, and once Bitcoin Core does it, everyone else will follow, yeah. Then it's pretty much a de facto standard, and everyone is going to have their own implementation in their own libraries. For now, if you want to use it, you probably want to bind to the C version, which is what we did. And write bindings from JavaScript and Python to the C version. All right, I hope that is clear now, because for the next step it's going to be really important. With just the music though, we have a multisig. A multisig is not an HDLC. So what do? We take the script from before with the if-else and rip it apart. The if tree, the if condition is now on the left side, and on the right side there's the time lock condition. So before we had an if and an else, now we have two separate scripts. And those scripts we call in Taproot leaves. So we have a Taproot tree with two leaves. One for the hash lock, one for the time lock. It's effectively the exact same script as before, but instead of if-else, we rip them apart into two separate ones we call leaves. And the beauty of Taproot is, if you want to execute one of the scripts, you only have to execute, first of all, the script itself, and only have to reveal the script you want to execute. So if I want to execute the time lock, I only have to show the time lock on chain. If you want to execute the hash lock, you only have to show the hash lock on chain. So instead of the if else and the whole script, you just have to show the part that is actually what you want to execute. So you save yourself from showing everything all the time to only what you need. In our case, it's very simple with just 2 scripts, but you could have hundreds or even thousands of scripts, and you only ever need to show what's relevant to you.
And each part of the script is linked to the version via the hash or the signature.
Exactly. So now we have a multisig, a common public key, and a tree of scripts with 2 possible scripts to execute. These 2 tie together in a sense that when you have this aggregated public key, you can so-called tweak it by the hash of the tree. So you take the scripts that you have in the tree, hash them, and hash the hashes again, and with that hash, you basically, very simplified, you multiply with the common aggregated public key, and then you have 2 ways of spending that public key. Either it's called key path by signing together, by like having a normal multisig and like we sign together, we agree, we sign together. Then we can spend with the key path. Key path means just with the key, we sign together, signature on chain, everything is good, coins can be spent. Now if we don't agree, which is really important for trustless protocols, if someone doesn't agree, becomes uncooperative, tries to steal, goes offline forever, things happen, we still have the so-called script path. And because we multiplied our aggregated public key with the hash of the scripts, we can prove that before the address was created, these scripts were known to everyone and everyone agreed with the scripts. So what we can do is a script path spend. We take the script, create a little proof that our script and the hash of it was in our public key, show the script on chain, push the variables required to fulfill all the conditions of the script and can spend. It's called script path spend. And that's a very common thing in Taproot, that you have 2 ways of spending, either with just a signature, in our case an aggregated one, a multisig, or the script path spend, which effectively means that you still have the option, in case someone doesn't agree, is offline, you can always fall back to executing the script on chain, revealing some information, a little bit more expensive because it's a bigger transaction, more operations, but it's still possible. So you always have these 2 options. You always want to do key path because it's cheaper and better for privacy, but to be able to be trustless and to have the option in case everything else fails, you can always fall back to, I know the script, I can prove it's in the address, it was included in the tree, and here are the variables required to make it return true and let me allow to spend the coins.
To do a summary.
Sure.
Is it the last slide or is it?
I think that's my last one before we do demos, yes.
En resumen, ¿qué ventajas tienen de Taproot? Con Taproot ahora tenemos dos métodos o dos maneras como podemos pagar un Bitcoin que está en nuestro caso en un swap. Con el KIPA hay que agregar los dos llaves públicas y luego hay que firmarlos y publicar. Esta es la mejor opción, el KIPA spend. Siempre quieres el KIPA spend, que requiere que tienes un canal de comunicación entre el Boltz y el usuario, pero es la método que preserva la privacidad mejor porque esta transacción on-chain es una transacción on-chain que no hay ningún poco de diferencia con cada otra transacción on-chain. No se puede saber que es un hash time of contract, no se puede saber que es parte de un atomic swap de Boltz, no se sabe. Este es porque este es el mejor parte. Siempre Boltz ahora está intentando hacer un KIPA spend. Si no funciona, cualquier razón como el usuario tiene problemas de conexión de internet y no sé qué, usa el script path spend. Y el script path spend con Taproot es mejor también. Significa, si hay que publicar algo, un parte del script, que es el hashtag o el timelock, solo hay que publicar un parte, no todo el script. Que significa más privacidad y significa más para todos.
And that transaction is already on-chain or is offline as in the Lightning Network?
Like here we talk about on-chain transactions. You cannot do on-chain transactions offline, but like, yeah.
It's a channel. The channel itself is an online transaction. An on-chain transaction.
It's an on-chain transaction, exactly. And here we just talk about when we have a swap address, an address of a swap, that is a Taproot address, how can one spend it? How can you like get your coins out of this address by spending it? And here you have the two options, the key puff spend or the script puff spend. It's just about when you like pay our Lightning invoice, we lock coins on-chain in the swap address, how can you get them? And these are the two options with Taproot swaps.
I guess in a normal Lightning transaction, non-swap transaction, the script path would be the force close. Or the way the force close would be.
Yes, right now a normal, like if you open Lightning channel today, it's not going to be Taproot, it's still going to be SegWit version 0, so the legacy effectively. But in a Taproot channel world, with which L&D is experimenting right now, it would be conceptually like a force close, yes. Yes, exactly. Like, yeah, a Taproot channel and L&D right now, if you force close, it's a script puff spend. Also the key puff spend. And that's like a common thing in all the Taproot protocols, that the cooperative thing to do, the nice thing to do, is the aggregated public key and signature. If something fails, like a force close, you go script puff.
Do you have?
Who was first? Yeah.
So for example, if you open a channel with Boltz and we make payments, and we never go on-chain, and the time passes by, in some point, we have a time block, so in some point, the channel is going to close. With the time block or not?
Like,
for example, if you have a time block of 1 year and the 1 year passes and you go on chain, the time block is going to close the channel.
yes, but that's true for every Lightning channel. If you have a pending HDLC, like a pending contract that's in the middle of the channel, either the recipient reveals the pre-image and everything goes through. In Lightning, there's also the option to cancel. Like we agree to cancel the payment and everything goes back and no force close. But if you run to the time lock, if enough time passes until the until the time lock that we agreed on expires, and we don't cancel, we don't settle, the channel is going to close. But we're not talking years here, it's more like a day at most until a Lightning channel force closes because of a pending HDLC. But that happens, not only with us, that happens with everyone. That's the nature of the Lightning Network, that if you have pending HDLCs that are not resolved, either by canceling or resolving, it's going to force close the channel, and the HDLC is going to go on-chain, and it's determined who is actually the one it belongs to.
You have to use a Taproot address in the swap, so you can use...
Yes. When we go back a little bit to SegWit v0, when we have the script, to create an address out of this, because addresses are very short. This is much longer than the address. What you do with SegWit version 0 is, you take the whole thing, hash it with SHA-256, and say op0, the hash. When you have Taproot, you take your public key, you tweak it with your scripts, and then you say op1 for SegWit version 1 Taproot, and then your public key. Or in our case, the tweaked aggregated public key, but basically a public key. And that's the difference between like pay to witness script hash, v0 SegWit, and version 1 SegWit. There's only, maybe you've seen pay to Taproot, p2tr, and that's just basically means op version 1, op1, and then some public key.
So it's cheaper to swap to the Taproot address with Boltz?
In a sense, yes and no. Because sending to a Taproot address is more expensive than like a legacy SegWit version 0 one, but spending from it is cheaper. And spending from it is so much cheaper that the overhead that sending to it is less. Yeah, in the end it's cheaper.
Can you elaborate more on the tweak part?
Yes.
Actually tweak the...
You tweak the public key, yes. When you when you want to add tab tree scripts to your public key in Taproot, it's called tweaking. And basically what you do is you take your public key and tweak it with the hash of the root of the tree of the script you want to add. That tweaked public key you take in the address of one tweaked public key, and when you spend from this address, you tweak your private key with the exact same thing and then sign with it. So basically it's like an equation, and you multiply both sides with the same thing. The equation is still true. Yeah.
Does this have some problem with transaction binning like the network have?
Yes, like basically every HDLC, every time lock based protocol has the same problem with pinning. That's like true for everything that has some kind of time lock component. Doesn't matter if it's a bridge or a lightning network or some other kind of concept that uses a time lock. As soon as you have some time component in there, you have a pinning problem. All right, and I think we're gonna do a real quick demo where we walk through code and see it work in practice.
Yeah, so we're going to get the computers and plug them.
Yep.
Okay, get the computers out, open your terminals.
We're gonna play around with Taproot a little bit now.
You can also sit on the table.
Like if you want to follow along, we prepared a small Git repo. It's written in JavaScript, so you need Node.js, preferably latest LTS version and npm to install dependencies. If you want to follow along, like do it live with us. But I will walk through the code and like show it all in here, so you won't miss out on too much. Yeah.
I would say that can clone it.
Yeah. If you want to follow along, clone it, and we'll walk through the code together.
Just search for Boltz Exchange GitHub, then you will get to our GitHub.
Are you ready?
Also a little QR code, easy to scan.
GitHub.com/Boltz
/boltz-exchange/boltz-demo. Yes, there's only one branch with its master. Once you have that repo cloned, npm install to install the required dependencies, which is like a Bitcoin library for creating transactions, the music library to create the aggregated public keys, and a bunch of other helper tools that makes the life as developer easier.
Node.js installed? No? You know how? Only like this. Oh, God, Mac. The Mac is
Homebrew. Was brauchst du? Node.js? Homebrew. Homebrew. Hold on, what you can do? Do you have a GitHub account?
Yeah.
Okay, you can use GitHub code spaces. That should have Node.
Browser?
Browser here, brief.
Yeah. What you can do?
No?
Can logged in, yeah, code? Code spaces.
Show that maybe on your create code space on master.
Yeah.
There we go.
As a fallback, if you don't have Node.js installed, you can like go on GitHub. If you are logged into GitHub, you can just like on our repo go on code spaces, create a new one, and that code space should have Node.js installed. Sure. Create a new one. Gonna load for a little second.
So if you don't know how to install Node.js, use this.
Yeah.
Log into your GitHub. You need to be logged in.
Log to GitHub, go on code spaces. That's gonna be a green button if you don't have one already. And click on it, wait for a little bit, and it's gonna set up everything you need for you. Yep. Takes a little while to get started, but then yep. Yep, there is Node.js. Once you have it cloned, do npm install in the repo, and it will install all the required dependencies. Or like, same goes for here, npm install in the terminal. It's gonna do its thing, install the required dependencies, and it's gonna run just fine. Yeah. I'm using this one. Readable? Readable? All right. So let's get started. Basically what we have in the top, in the first, like, I don't know, 22 lines, is just dependencies. Because we just talked about it. These are bindings from JavaScript, which we are using to the Blockstream C library for the music to signature aggregation. Just like, not really relevant to us, but that's what it is. And here we have like a bunch of Bitcoin, transaction creation, helper functions, classes, and basically this setup we need to do swaps and create Bitcoin transactions. Then we have our API endpoint, which is API testnet Boltz exchange, and we're going to use testnet because like if something goes wrong, testnet coins are not as bad to lose as mainnet coins. In line 28, we specify the amount we want to swap. In our case, it's 50,000, so 50,000 Satoshis. We're going to move from Lightning to the main chain. Destination address is where we want to receive our on-chain coins on the main chain on testnet. If you have a main chain wallet, put your address in the quotes. If you don't, just put to the same address and it's going to be fine. It's an address of ours and we consider it a donation of testnet coins. All right, and we tell our Bitcoin library we're going to use the network testnet for our testnet swap, so yeah. Some initialization for libraries and cryptography, but here it gets interesting. In line 40, we create a pre-image. This is the secret for our hash lock. And that hash lock we're going to reveal to Boltz later for the aggregated signature, but for now we just save it in a variable, and with that we create the swap. In our case it's just like 32 random bytes, good enough for our purposes. Also, so that we can sign things and sign things together, we need keys, and for that we just make random keys. Not recommended for production, but for our example here, good enough. All right. The next thing we are doing is Axios is an HTTP helper library, and we do a post request, which means HTTP method post. And what we basically do is we send our API a bunch of values. Invoice amount, how much you want to swap. From to BTC, so from Lightning BTC to on-chain BTC. Our public key we give to our API 2, so that they can aggregate it and create an address. And we also give it the SHA-256 hash of our pre-image. We don't reveal the secret yet, we just give it the hash so that it can create the hash lock. Then we do some console logging so that we can track what's going on. And here we come to the communication protocol. I mentioned before that you can use whatever you want to communicate and create the common signature, the aggregated signature. In our case here, we use a WebSocket because that's faster and super nice for bidirectional communication. And a WebSocket, we send a message that it should inform us about updates about the swap we just created. For that we have a swap ID, which is like a unique identifier for every swap, and we tell the WebSocket, hey, whenever something happens, please tell me. When something happens, and we get a message from the WebSocket, we parse it, do some more console logging to see what's going on, live in the CLI. And then we have in our API a couple so-called status updates. A status update is basically telling you as a client of our API what's the status of the swap, what are you supposed to do, what did we just do, and what's the next step that's to be done. Swap.created is pretty self-explanatory, I think. We just created a swap from Lightning to the main chain, and we are printing, waiting for invoice to be paid in the console. It gets more interesting with transaction.mempool. Transaction.mempool means the Lightning invoice has been paid, and we set an on-chain transaction ready for you to claim, ready for you to sweep through your own wallet. And the transaction is in the mempool. You might want to wait for one confirmation, but in our simple example here, to make it quick and reliable, we are just going to spend the funds from the mempool to our destination wallet from above. And now we get into the actual interesting cryptography and Bitcoin part, where we do craft a transaction that sweeps the swap address to our own address via music2 and the cooperative common signature. First of all, so that we can sign and verify that the signature is correct, we need to parse and know not only our own public key that we created, but also the public key of Boltz, of the other side of the multisig. And for that we just take the response of the API, parse it as buffer, and have then here like the public key as bytes from Boltz. Then we create a music signing session. This just initializes the library that we need. This is our keys that we sign with. This is a random bytes, basically a session ID to make it the protocol secure. Not going to get into the details here, but basically we use random bytes here, which is fine. And then we tell it our public key is an aggregation of the public key of Boltz and ours. Here comes the tweaking part, where we have a nice wrapper function for tweaking the multisig. We pass it the multisig, and we call it swap tree serializer. With that, we take the JSON response of the API, the tab tree, which we call swap tree for like our swap, deserialize it into like the internal data structures. And what happens behind the scenes in this function is it takes the multisig, the music, gets the aggregated public key, and then multiplies it with the hash of the scripts that we just created. So now we have pretty much everything set up for our signing session, and we know our aggregated public key, and we know the tweak, and we have tweaked our key. So only thing missing now is the actual transaction, and for that we parse the WebSocket like the WebSocket message, and read the transaction, the raw transaction as a message, and parse it. Then we found the lookup transaction, which just means the coins have been sent on chain, and that transaction we parse. We detect which output of the transaction belongs to us by looking up the tweaked key is our tweaked public key, and this is the transaction. This function goes through all the outputs and finds the one that we can claim and sweep to our own wallet. When we find our output that we want to sweep to ourselves, we construct a claim transaction. Claim transaction means from the coins we sent, you sweep it to yourself. For that, we give it the output that it should sweep, our keys, our pre-image. We tell it cooperative true, which means we want to not broadcast immediately, we want to do a signing session together. The output type is Taproot. We want to spend this transaction. We want to spend to our destination address, and for that we have to decode the address into the actual script, specify the fee, and this gives us basically the boilerplate of the transaction. The raw thing that has everything in it, apart from the final signature that we create together. For getting the final signature, we have another API endpoint, and we just tell it, of my transaction, sign the index 0. So the 0th input, we have a transaction with one input, one output, sign the 0th input. This is my pre-image. This is my public nonce, which is an internal detail of how music works. But we give it our transaction and our pre-image. It gives us back the nonce of the other side, which we aggregate. The nonces are pretty much relevant for like a single signing session, that two signing sessions belong together. Internal detail of music not really relevant here, so we're going to skip over that. We tell our music what we want to sign. We add the partial signature of Boltz. We sign our partial signature. And in the witness of our input of the transaction, we set the aggregated partials, which means that we told Boltz our pre-image, it gave us back its partial signature. We set up our multisig to be able to create our partial signature. And in our transaction, we just set the witness to the aggregated signature, which is basically the two partials, one for Boltz from the API, one from our side, put together, and that we stick into the witness. In the very end, we also have an API endpoint to like broadcast the transaction, but you could do that with basically any Bitcoin node or Block Explorer, whatever you want. It's just that, like, for simplicity reasons, we took our own API. And that's it. That's all there is to music and tweaking and scripting and stuff. And what we're going to do now...
Sorry, I have a question about
Yeah, sure.
Well, you started everything once you see the transaction method, right?
Yes.
What if in that moment is go through the loop?
Like if you build your own API client, you can wait for a confirmation. You can wait for 10 confirmations. You can wait for an hour, whatever you like. It's just like for our demo purposes, it's much nicer to like do it instantly.
Sure. But I guess at some point the swap created by you expires.
Yes.
So how much time is that?
Depends on the direction. For this direction from Lightning to Maintain, it's 24 hours. Yeah, but like if you build your own client, we have an extra status event for transaction confirmed, which means it's included in the block. You can like wait, if you have your own node to check or some API, you can wait for 6 blocks, whatever you like. It's just that for a demo, it's very annoying to wait for 6 blocks, so we just do it instantly.
On maintain you wait for one confirmation.
Yeah. All right. So once you have npm installed and the dependency is installed, I'm gonna make this one even bigger so that everyone can see. With Node.js, we execute our swap.js. What you should get is something like this, where you get the news, a console log output of, hey, this is your freshly created swap. It has this ID. This much we're gonna send on chain. And this is your Lightning invoice for the swap. Afterwards, it should tell you got a WebSocket update, that the swap has been created, and it's waiting for the invoice to be paid. All right? And now all we need is just some testnet wallet to pay the actual invoice. Hold on. I have like a Phoenix wallet on testnet here, and like if you have an invoice you want to be paid, Killian or I could pay it. Like for that.
You can go to qr.michael1011.at
and create live QR codes live, yeah.
Paste the invoice string there and I will pay it.
Yeah.
Okay. QR. Michael.
All right, like a little bit of a coordination problem. All right, like once you have, this is the invoice from above as QR code. I'm just gonna scan it with my Phoenix testnet real quick, and when I scan and pay the thing, to the output, transaction has gone through on my Phoenix testnet, and we got the updates we were expecting. First, we got the transaction mempool, and like this is the transaction ID. This is the whole transaction that the Boltz backend API sent to the mempool. This is the transaction. It created a claim transaction, and in the end, the swap settled. Now, if you look at the block explorer, like for example, mempool space testnet, we're gonna see our transactions. First of all, this one, and then also one spending from it.
Why not be here? I think so. Not everybody is saying step.
Yeah. Just gonna prepare a little bit. All right.
So one thing I want to make clear, because I just realized I should have said that this is an atomic swap.
Yeah. This is an atomic swap.
The pre-image thing that we are talking about is the very basic, on HDLCs, are the very basic concept of an atomic swap. What we just did is an atomic swap.
Yeah.
We lock two payments, and then we unlock them at the same time with
Basically, what like it's very fast because we don't wait for confirmation. But like when you pay the Lightning invoice, it's going to be pending until your code does this and creates the claim transaction. If you like put a return before that and pay the invoice, it's going to be stuck and go eventually until the time lock path and fail. So yeah, atomic swaps. It's basically that's what we just did. All right. And one last thing I want to show is when you have this console output, you will see a line called got lookup transaction, and afterwards there's a hash. In my case, it's 559E something. If you copy that and put it into a testnet explorer, like for example mempool space/testnet, you can see the transaction. And you can see the outputs. And both of our outputs are version 1 pay to Taproot. The one with 50K, almost 50K sats was mine. That was my swap. And the transaction here, I created in my little console application. When we look into the input, it's just a signature. And that signature is the cooperative Music 2 signature. We aggregated and put the witness, and if you didn't know that it was a swap and all the things happening behind the scenes, if you just look at the block explorer, there is nothing to see, just a normal signature. If I do a Bitcoin Core single sig spend, also it's a signature, and that's the beauty of Taproot. You can abstract it all and hide it all away into the single signature. Doesn't matter how complex the logic behind the scenes actually is. All you see on chain is like this 64 bytes of signature.
Maybe we can do one more quick mainnet for people to see that this complicated thing can be a website. Let's do a liquid swap.
On mainnet. Do you have a mainnet wallet at hand? Send me an address. All right.
Very quickly, you can go back to
Sure.
the type. The transaction type is V1.
P2TR. V version, second version 1 pay to Taproot.
This is not constraint about the privacy, because if you know that this transaction comes from this kind of
Like, we are not the only ones using V1 pay to Taproot. There are more and more wallets and services switching to Taproot, and like in the end, right now there are not that many. But if everyone is using it, you hide in the crowd.
It's actually not that bad, I think. So the idea is that in future everyone uses Taproot.
but right now you
Right now,
Phoenix is
Phoenix is starting to use it.
But it's very difficult.
Very little, yeah. Like
But in the future,
yes.
Everybody
Uses Taproot and everything looks the same. Like right now it's Lightning Loop, it's Phoenix, it's BitGo for the internal wallets, a little bit at least. It's us, it's a bunch of ordinals, like all the ordinals are also paid to Taproot. But good or bad, it makes you hide in the crowd. And the higher the Taproot adoption, the better it is for privacy, because if you're the only one, yeah, it must be you. If you're one in a million, you hide much better.
One reason why we waited until we only launched this in January, and we couldn't really launch it much earlier because, I mean, the libraries, music, and stuff, they were not that stable before, now they're good. But the second reason also is, in a swap, we will actually, but we have to show a Taproot address, and the sending wallet needs to support sending to this Taproot asset. And that was an issue in the past, like the adoption has been kind of slow, it's been 2 years now, but by now there's only Coinbase
and some other obscure exchanges, yeah.
Wallet that cannot send to Taproot. All the rest already supports sending to Taproot.
Yeah. You can receive to any address, but if you want to go from on-chain to Lightning, we show your Taproot address, and you're going to send that, be able to send to that.
Why they classify it as another address, but of course their wallet supports it, it's just the front end that says.
Yeah. All right, and like...
another consideration about the fingerprint that maybe you need to have in mind about how to identify transactions in order to have a less privacy.
The other thing to consider is, like, of course, the timing attack. In a sense that you see there was a transaction to Taproot at output, which was immediately sent in this weird transaction kind with one input, one output. That's the other privacy gotcha, a timing attack basically. That you have like these two transactions happening in quick succession, which is a giveaway. Could be a giveaway that it's some protocol behind the scenes doing its thing. So it's not perfectly private, it's not an alternative to coin joins, but like this is much better than having a huge script on chain.
But we could change that.
Yeah.
We could change the claiming logic that it leaves some time until claiming,
yeah.
And you're ready. So you basically don't, however, you want to have a nice experience and immediately success, great. But if you have a rebalancing, channel rebalancing client running, you might say, I can 3 swaps and claim them all together in the evening. You know? Okay.
Yeah, like there's
correlation of the
there's lots of flexibility you can do, but either way you do it, it's not an alternative to a coin join or some other real good privacy solution. It's more like that this is more private than it was before, but still not the privacy solution you want to rely on. It's better, but not far from perfect. Yeah. All right, and the last thing I'm going to show is that like this code we have here, in a little bit more safe, a little bit more persisting values and whatnot, is in our web app, Boltz Exchange. And in the end, all this UI does, all the things it's doing, is pretty much using the code we just did very similarly. Like it's the same thing basically. Should we do a demo real quick?
Okay.
All right, swap to liquid, I guess.
Yes. I send you a link.
Hold on, I don't want to leak all of my signal chats. Let me get the address real quick. Yeah, privacy reasons, also for the presenter.
I just told him to cut this part from the video, but you had it also.
Yeah.
Much better for me.
Yeah, it's just easier this way. All right, the same thing we just did with the music, the tweaking and whatnot, also exists on... Hold on, yeah, also exists on Liquid. And for the quick demo, we're gonna use Liquid. So we basically just say, hey, I wanna swap from Lightning to Liquid. It just adds like 1,000 Satoshis, not a lot, just for demo purposes. Put in our address. It shows me a QR code and the Lightning invoice.
The same thing you did.
Same thing you did. Just like a little bit of a nicer UI.
Now I'm going with my Phoenix and paying it.
Transactions in the mempool, broadcasting claim transaction, settled. And when we look at the block explorer for that, take me a second. Come on, do your thing. Yeah, there it is. When we look at the liquid transaction, the claim transaction we just did, we have the exact same thing, that it's version 1 paid to Taproot, just the signature in the input, and as a nice privacy benefit on Liquid, we also have in the output the amount confidential, so secret.
Why was it so fast?
Because we do the same thing as we did in the CLI, we accept zero-conf on Liquid because that's on Liquid it's fine. There is no mempool for RBF.
Yeah, I just mentioned that as well. So we accept zero-conf for Liquid because Liquid is designed for zero-conf to be safe, also in the future.
Yeah, there is no mempool full RBF, and like it's a property of Liquid that zero-conf is safe. Up to a certain amount, and for the thousands of tokens we did, it's considered safe on Liquid. Yep. I think that concludes today's theory lesson in Taproot and a little bit of.
Who made it through? Who made the swap on the CLI?
I made the request, but they didn't press.
Hold on. Let me give you some test results then. You have the invoice?
Yeah, but I didn't create the.
Yeah, like it's hard for me to scan something. I don't know. Like just Google QR code creator or something, and then I can pay it for you real quick. Just, I don't know, QR code creator.
So as you can see, it's an API. We just did API calls, but it's not as easy as
Whatever, yeah. And put in the invoice.
I sent you this. You sent
Yeah.
You have to do some crypto magic and sign it.
Is it the whole invoice?
That's
Let me check.
Yes.
Should be, okay.
If you want to integrate,
Just gonna scan that. Pay.
you have to kind of. But our idea is
There you go.
we have nicely documented the main key parts. So actually, what we did, the code that you are running in the demo is more or less one-to-one in our documentation. So you can have an example of TypeScript for goals. You don't need to think and come up with this all by yourself, but you can use core example, and then you adjust a little bit and tweak where you need to.
Basically, a library that integrates and it's made even more easy. It was easy.
Like
Even more.
the thing is,
And we also have our Go client that we would need to convert into a library.
you can use this library. The thing is that like when we look at the libraries we are using, there's one library from which we import a lot, and it's called Boltz core. That's our core library in TypeScript, and like it might not look like it, but it's abstracting so much away from you. Just the hashing of the tree is like its own little madness.
We have this code already so much better.
Yeah. And like these kind of things that we did, for example, when do you create the music? When do you do the transaction aggregation? And like when do you do these things? These are design choices for you to make as a developer. So we didn't want to, we use this library in our backend, on our server, on the website, and we do these things in different places. So we didn't want to make it even easier and make the design decisions in the library. We left you as a developer all the decisions, when to do what and how to do them, because we needed to make these choices ourselves in different places, in a different way. So even easier is possible, but then you're more restricted to a certain flow we force on you. So this pretty much is already a really high level of abstraction, but it still allows you to do whatever you want, whenever you want, how you want. All right.
Because the integrations that we have with the API, they're very different use cases. They're not all like our web app, right? So, for example, if you take Aqua Wallet, they do things very differently. They need to think clearly when is the correct time to play, when is the correct, you don't want to take the choice away.
All right.
That was cool.
Questions?
Well, all right, I have a lot of questions.